Very good morning, friends. Once again, I am here to tinker you about this electrodynamics. Up till now, we have talked about electrostatic. Now it is electrodynamics. Electro here means charge, electric charge. Dynamics means in motion. What will happen when the charged particle will be in the motion? That's what we are going to talk about in this particular topic, right? Electric charge itself means, now what is that? Simply transfer of electron. So first topic here is electric current. What is electric current first of all? So in natural state, what is happening? Suppose I am having a conductor here, a large number of free electrons will be there, moving in all possible directions. Remember, that's what we call random motion. In random motion, the velocity of a particle is, as we have done in kinetic theory of gases, it is 3 kT by m, right? Which we used to say VRMS. And the random motion of an electron is of the range of very high value, 5 meter per second. But because of this randomness, what happens? The average velocity is always 0, right? And mean free path in this case is of the range of 10 angstrom. So this is the randomness. Because of the randomness, the average velocity is 0. So net impact is 0. There will be no flow of electron. Nothing will happen, right? But in the same system, if I apply some external source, we will talk later on what sort of external source. When some external source is applied, an external source, right, just like a battery cell. So what happened? These randomly distributed electrons try to get aligned. They try to flow in a particular direction. Right? When this external source is applied, they start flowing in a particular direction like this, and with a small velocity, Vd we call it, that is drift velocity. Why it is drift, we will talk about it later on. Drift velocity. And this drift velocity is of very low value, 10 to the power minus 4 meter per second. See the variation. But because of this drift velocity, what happens? An electric current is produced. Current start flowing in a direction opposite to the flow of current, free electrons. Because of this external source, what happened? Free electrons get aligned and try to flow in a particular direction. Remember, this flow of free electron in a particular direction through a conductor, when some external source is applied, is known as electric current. Remember always, now in 12th standard, what is electric current? It is the flow of free electrons through the conductor. in a particular direction when some external source is applied. This is the actual definition of current, flow of free electrons. Up till now, in 10th standard, what we have read that rate of flow of charge. Mathematically, it is correct. So, as the electrons are flowing in a particular direction, so simply a flow of electron will produce a charge. So, mathematically, we represent the current by small I, and it is nothing but it is Q by a T, where Q is the electric charge and T is the time. Therefore, mathematically, the rate of flow of electric charge is known as electric current. This is the mathematical definition. But what actually the current is, it is the flow of free electrons. So far as unit is concerned, charge is measured in terms of coulomb and T time is per second. Coulomb per second is given a new name, ampere. Ampere. SI unit of electric current is ampere. Remember, it is the standard unit of electricity, ampere, right? This is electric current. Now, question arises, in some substances, current is flowing, in some not, in some it is partial flow. What is that? After electric current, we have got a mathematical. Okay, one more thing. Remember, electric current is a scalar quantity. Though we represent it by the arrow in terms of DC current, but it is a scalar quantity. Question arises, why? Because it does not follow the vector's laws of addition or subtraction. What does it mean? Suppose 2 ampere current is coming from this direction, 3 from this direction, or I could say here, how much current will be there according to this. Instead of applying the laws of addition, vector's laws of addition, simply get 5 ampere, right? It doesn't follow the vector's laws of addition. So far as direction is concerned, it simply represents a direction opposite to the direction of flow of free electron through a conductor. After this electric current, we have quantity electric current density. Suppose a current is flowing through a conductor of area of cross section. A is the area of cross section of this wire, and current is flowing it. So this current density J mathematically is I upon A. Electric current per unit area of cross section. Electric current flowing through a unit area of cross section of a wire, right? It is a scalar quantity. Do remember this fact. It is a vector quantity. Current is a scalar, but current density is a vector quantity whose direction is always towards the electric field direction which we are applying. In some mathematical formation, I can be calculated with J dot ds. J dot ds, where J is the current density and ds will be the area of cross section of that one, right? So that's how we calculate it. If you want to calculate this current, if J and ds are given in terms of vector, we can simply use the dot product, the scalar product of current density and the surface area vector. Now, how to relate what is drift velocity and how to relate these quantities, that's what we want to do. So let us consider a metal wire of area of cross section A, I is the current flowing through it, and Vd be the drift velocity, and small n be the electron density, that is number of free electron per unit volume, right? And Vd is the drift velocity. How to interrelate that? That's what we want to do. So what is happening? If Vd is the drift velocity, actually drift velocity is simply a drift actually. We will talk it later on. Constant speed in one way acquired by free electron. If it is a constant speed, then what will be the distance traversed? By the free electron in 1 second. How much? This Vd into 1 will simply give you Vd. Means a particular distance will be traversed by the free electron in 1. Suppose this is the distance. Question arises, how much volume will it acquire? Look, this much. Volume we have got pi r square h. If you remember, the area of cross section into distance, that is Vd. It will become AVd. The distance travelled by the electron in 1 second will be what? Speed into time, Vd into 1, that is Vd. Same way, the volume acquired by the electron in 1 second, it will be AVd, this much. This will be AVd. This is the volume acquired by the free electrons in 1 second. Now, as the electron density is n, so how many electrons will be there? So, number of electrons moving in 1 second will be what? Electron density is n and the volume is AVd. This is the number of electron. And according to quantization, what we have? Q equal to n into E. Number of electron multiplied by the fundamental charge. Right? Will give you the electric charge. So, electric charge flowing through the wire in 1 second. What will it be? Total number of free electrons and the fundamental charge. Total number of electrons we have got NaVd into E. Now, if I just go through this particular article, what we got in the last is electric charge flowing through the wire in 1 second. What does it mean? It will give you the rate of flow of electric charge. And by the definition of current, this rate of flow of electric charge is what? The electric current itself. And how much we have got it? It is NEAVD. It means we got a relation I equal to NEAVD. This is the relation between current and the drift velocity, right? And actually our requirement is what? Relation between current density and the drift velocity. So we will just make an adjustment. I upon A can be written as NEVD, and this I upon A is now J. J is NEVD. This is the relation between current density, drift velocity, right? N is the electron density, E is the fundamental charge, and most of the time few numericals are there. So be careful of this article. It is simply a poem in itself. Now, based on the electron density, we divide matter into three basic parts. If you have heard about it, conductor, bed conductor or insulators, and third part is what? Semiconductor, right? And fourth one more is there, that is superconductor. Question arises, what is conductor? Are those substances which have very high electron density. Of the range of 10 to the power 29 per meter cube. Means number of electron will be very high, so what will happen? There will be an easy flow of electric current. Through them, right? So far as example is concerned, silver is the best conductor, except all metals. So conductors are those substances which have very high electron density, and due to that they easily allow the electric current to flow through them, right? Second one is insulator. In insulator, negligible number, we can't write on 0, negligible number of free electrons. We did talk about dielectrics, so remember, all the dielectrics are insulator, but all insulators are not dielectric. Negligible number of free electrons are there, so there is no flow of electric current in normal condition, right? Then in between these two, one more phase is there, we call it semiconductor. Later on we have a complete chapter on it, but here we just introduce it. Semiconductors are having very few number of free electrons. Few number of free electrons. Since number of free electrons is very few, so there is only a partial flow of current. Example is silicon, germanium, if you have read, right? These three basic category: conductors, insulators, semiconductors, right? Conductors allows electric current to flow through them easily. Insulator almost null, semiconductor partial. One more state we were talking about, superconductor. What is it? So while dealing with cryogenic science, what Kamalin Owens found that if the temperature of a conductor is taken up to the absolute zero, an order of, you can say, absolute zero, then what happens? All of a sudden, the resistance, we will take later on, resistance of the conductor, some conductor, particular one, not all, becomes almost zero, and due to that, their conductivity tends towards infinity. Such a state is known as superconductor. Mercury, remember this factor, mercury does behave like that. Like a superconductor. Remember, at a temperature 4 Kelvin, remember this value, 4 Kelvin, it is very low, minus 269 degrees Celsius. Practically, this is not possible. So this is one of the state, superconductor. At low temperature, some conductors behaves like a superconductor. Now question arises, few are allowing electric current to pass, few are not, and few are partially. What is the reason behind that? Which factor is opposing that? In physics, in electrodynamics, we introduce about resistance. Resistance means what? Name it clear. To resist means to oppose. Question arises, whom? The flow of electric current. Right? It means, what is resistance? It is an internal property, remember. An internal property, inherent, inborn, of a conductor to oppose the flow of electric current through it. Right? So this is the definition of resistance. Now question arises, on what physical factor this resistance does depend. From the experimental data, it is found that suppose I am having a wire will have its own area of cross section as well as its own length. These are the two basic factors on which the resistance depends. It is found that, first case, resistance is always directly proportional to length. R directly proportional to L. This is called length rule. But remember, this is if and only if A is constant. Means this rule will follow if the wire is of same area of cross section. Right? Then we can write down R1 upon R2 equal to L1 upon L2. if A is constant. Remember, second factor, resistance be represented by capital R is inversely proportional to A. A is the area of cross section, means thicker with the wire, smaller will be the resistance. Opposite side fact. Remember this one. Thicker be the wire, smaller will be the resistance, and vice versa. Means thinner with the wire, higher will be the resistance. Again, the question is saying that it is applicable if and only if I am considering L to be constant. R is inversely proportional to A independently if and only if L is constant. Then it comes out to be R1 by R2 equal to A2 by A1. Condition is that L should be constant. If I vary the length, naturally area of cross section will also vary, and vice versa. So we will apply these two laws all together. Instead of using independently, what we will do, we will use this law together. R directly proportional to L upon A. Right? Means if I am varying L, A will also vary. If I vary A, L will also vary. So this will be R directly proportional. When in physics, whenever we have a sign of proportionality, we always use a constant. Here the constant is rho. Be careful about this particular quantity, rho. Very important in experimental point of view. Rho. So this rho is a constant known as, remember, specific resistance or resistivity. Both are the same thing. Specific resistance or resistivity. Remember, of what? Of the metal of the wire. Remember, emphasizing on this word, metal of the wire. Means there is no rule for length and area. It is simply constant for metal of the wire. So far as unit as resistance is concerned, just to facilitate George Simon Ohm, then its unit is ohm. Symbol is like this, right? So by using this formulation, our rho comes out to be R A by L. What will be its unit? For resistance, I am writing ohm. For area, meter square. For length, meter. So if I cancel it, what we will get? Ohm meter. Remember, unit of specific resistance or resistivity is ohm into meter. Ohm meter. Right? Now, how to define this rho? Let A be 1 square unit and L be 1 unit length. Then what will happen? If you substitute here, then rho comes out to be R. What does it mean? The specific resistance or resistivity of a metal of a wire is defined as the resistance of a wire of unit length having unit area of cross section. Remember, this we have already done in class 10th also so many times, but still in class 12th also it is very important quantity. Specific resistance of the metal, be careful while writing it, metal of a wire is defined as the resistance of a wire of unit length having unit area of cross section. That's how we define it. So far as mathematically value is concerned, rho is R A by L. A can also be written as pi R square by L. That's how we calculate rho. Where R is the small r is the radius of the wire and L is the length of the wire. Right? Now question arises, what is the difference between the resistance and the specific resistance when both are we are adding rho equal R? Remember, R does vary with respect to area of cross section and length, while rho is what? For the metal. Means for a particular metal, the rho will be constant. Rho of aluminum, if I say, it is going to remain constant, whatever be its area of cross section or length. Same way, copper will have its own specific resistance, hardly matters how long or how thick it is. So this is the key difference. Now how R varies with respect to length and area of cross section, let's do some basic questions you could say. For instance, if the wire is stretched, you could say, in such a way that its length get doubled, right? What will be its new resistance? That's what we want to find out. Right? Suppose I am having a wire of length L and area of cross section A. What will be its resistance? According to formula, it will be rho L via A. Now, according to question, this length is now doubled. This wire is stretched and length is doubled. L dash I could say it is now 2L. Question arises, if I am stretching it, if I am increasing its length, naturally it will become thinner. Means its area of cross section will also vary. Let it be A dash. We don't know about A dash how much it is going to vary. And because of that, new resistance will be R dash. Question arises, how much will be the R dash? R dash will be rho L dash via A dash. Rho L dash is twice of L, but A dash we don't know. That's what we want to find out. Now, while stretching the wire, which mathematical factor is going to remain constant? Question arises that. So, if you stretch the wire, mass of the wire is not going to vary. Whatever be the initial mass will be the final mass. Mm dash, I could say. If initial mass is m and final is m, both will be same. Mass is not going to vary. And mass is what? Density. And metal is of same, so density will be same. We left with volume. As metal is same, so density will be cancelled. We left with volume equal to volume. What is the initial volume? It is A into L. What is the final volume? A dash into L dash. A into L. A dash we don't know, but L dash we know it is 2L. So L cancelled. We left with A dash comes out to be A by 2. Means the area of cross section will become half of the initial value. So what will be the new resistance? R dash will be rho L dash via A dash. Rho L dash is 2L, A dash is A via 2, and what we got? 4 times of rho L via A. And what is this rho L via A? It is R. It will become 4 times of the initial resistance. Most of the time they give a kick here. How much percentage is it going to vary? That is, it is being increased. So what will be percentage increase? Remember, it will be R dash minus R by original value R into 100. And it comes out to be 300%. Most of the time you people use to write 400%. But remember, it is asking percentage increase. R, 1 rupee you are already having, and now you have got 4 rupees. So how much more? That is 3 only. That's why it is 300%. In terms of length, if the resistance, new resistance get varied by n square times, remember, this is the key factor. If you double the length, resistance will increase, will become 4 times. If you triple it, it will become 9 times, like this only. This is with respect to length. Now, if the area of cross section is varied, then what is going to happen? Same thing can be repeat here. Is if the wire is, or I could say change the sentence. Suppose I am having a wire of area of cross section L and length L, and R is the original resistance. R is what? Rho L by A. Somehow what we did, the wire is molded in such a way that its area of cross section becomes twice of the initial one, right? What will be the new length? We don't know. Let it be L dash. Resistance will be R dash, right? So new resistance R dash will be rho L dash by A dash. L dash we know, A dash we know, but L dash we don't. So again, while doing this, the volume is not going to vary. V is equal to V dash. Initial volume is equal to final volume. Initial volume is A into L, and final volume is A dash into L dash, right? And A dash we got 2A into L dash. A is cancelled. L dash comes out to be L by R2, right? So what will be the new resistance? R dash is equal to rho L dash by A dash. Rho L dash is L by R2. A dash is 2A, and we will get 1 by R4 rho L by A. Remember, this is 1 by R4 times of R, right? 1/4 of the initial resistance, right? In this, what will be the rule? R dash will be 1 upon n square of R if area of cross section is varied, right? And how much percentage decrease will be there? Remember, it is decreasing. On R dash, it will become R minus R dash by R into 100. It comes out to be 75%. I guess we calculate it. Very simple. In class 10th also we have done it. One more twist, instead of area of cross section, if the radius of the wire is varied, if the radius of the wire is doubled. Remember. So what we have? R is rho L by A. As the question is in terms of area, radius, so we will write down this formula in terms of rho L by pi R square, right? And after doubling the resistance, radius, R dash will be rho L dash by A dash. It will be rho L dash by pi R dash square. This is the new resistance. Same process, volume will remain same. It is A into L. A dash into L dash. A is pi R square into L. And A dash, remember, it is pi r dash. Pi r dash square into L dash. What is r dash? Here r dash is given twice of r. This is the given factor. It's doubled. So if I substitute it here, what I will get? Pi can be cancelled. R square into L. It will be 2r square into L dash. Right? So r square into L is equal to 4r square into L dash. So r square can be cancelled. We left with L dash will be L via 4. Right? If L dash is L via 4, so what will be r dash? Rho L dash via pi r dash, its square. Rho L dash comes out to be L via 4 pi r dash I am having 2r its whole square, and it comes out to be 1 by 16 times of rho L by 8, or 1 by 16 times of r. That's how we do it. We can vary the radius, we can vary the area, we can vary the length and calculate the new resistance. Right? Thank you. Now, as in the beginning we did talk about that, when some external source is applied, question arises, what is that external source? Right? As in a classroom, student used to roam like anything, but as soon as the teacher enters, what happens? Everything get aligned and a proper classroom is maintained. Same way here, electrons were moving in the all possible direction. When we use the word when some external source, what is that external source? Here the basic is electric cell. You might be knowing voltaic cell, Lagrange cell, Daniell cell, and dry cell also. Electric cell. What is an electric cell? In layman terms, just a device which converts chemical energy into electric energy. In lower class it is like that. But here what is happening? We are saying that this is the external source which is aligning the free electrons. Right? This is the electric cell. We apply it like this and the free electron get aligned and try to flow in a particular direction which produces the current. So what is happening? In physics, we simply term it an arrangement, an electric cell, an arrangement to make a continuous flow of electric current throughout the circuit, including the cell. Right? Just an arrangement to make a continuous flow of electric current throughout the circuit, including the cell. This is electric cell, right? Current always flows from higher potential to lower. Remember, this positive itself is higher potential, negative is lower potential. Current always flows from higher to lower, right? And here we define electromotive force, right? Old term, EMF, of a cell. What is that? Right? To flow this electric current throughout the circuit, including the cell, naturally some energy is required. So this electromotive cell or EMF of a cell, we denote it by capital E, is nothing but total amount of work done to flow a unit charge throughout the circuit, including the cell. EMF is the total energy required to flow a unit charge throughout the circuit, including the cell. If definition is concerned, it is the energy or work done, you could say, required to flow a unit charge throughout the circuit, including the cell. Remember, means this EMF is the total energy which flow the charge, and so far as its unit is concerned, it is again joule per coulomb is nothing but volt. The unit of EMF is volt. One more term we define, battery, electric battery. It is nothing but combination of two or more than two cells. If you combine two or more than two cells, it forms a battery, right? This is EMF. Then we define potential difference, though we have done in electrostatic, but here also we will define potential difference. Again, V is W A to B by Q, if you don't remember. Amount of work done to flow a unit charge from a point of higher potential. Remember, to flow a unit charge from a point of higher potential to a point of lower potential in an electric circuit. Right? EMF is for the whole circuit and potential difference for a part of that. Right? Thank you and have a nice day. This is the basic. All right. Thank you.